Alright guys, hi, welcome to another tutorial. We're going to be using percentages as conversion factors, and a lot of times when you guys do a lab in general chemistry or fundamentals chemistry, you will easily do a separations lab or something that you have to utilize percentages as conversion factors. So let's go ahead and get started on that. Okay, let's do the simplest case scenario. Okay, so let's say that you have a mixture and you've got component A, B, and C in it, and you're given the masses of each of these components. How do you calculate the percentage of A, B, and C? So recall, when you calculate a percentage, it is the mass of the part divided by the mass of the whole times 100, right? So in this case, let's start out by working on A. So you do the mass of A, component A, divided by the total mass of mixture. So, and then you would multiply this by 100, because if you just did that, you would get a fraction, right? So problem here is, do I give you the mass of the whole here directly? Not really, right? You got to figure it out yourself. So let's do a calculation here. Here's the component A, this is component B, and this is component C. So let's do the total mass calculation up here. So we would do 1.2354 grams plus 3.2545 grams plus 5.5875 grams. And so this will give you a total of 10.0774 grams. So whenever y'all are trying to figure out the mass percent for A, we're going to do the mass of A, which is 1.2354 grams divided by the mass of the total, which is 10.0774 grams times 100%. That should get you 12.259% of component A. So essentially what you're saying based on these numbers is that your mixture is 12.259% of component A. Okay, now guys, if we were going to do component B, we would do the same thing. So I'm going to erase this here, and we're going to work on component B this time. Notice the only thing I'm going to change is just this part right here. The percent of B is the mass of component B, but still divided by the total mass of mixture. So in this case, it'll be 3.2545 grams on the top multiplied by 100 here. So that should have gotten you 32.295% B. By the way, guys, why am I rounding here to, if you notice, that's 5 sig figs. Pay attention to this because it's very important in chemistry, right? So this number has 5 sig figs here. This one has 5 as well. So if it didn't, you'd always go with the least number of significant figures. Remember, the 100 here does not count for sig figs, because that's by definition. When we say percentage, we mean percent per 100. So that's by definition. And remember, that's an exact number. It does not count for your significant figures because it has unlimited number of significant figures. Okay? Now, guys, I want you to think about something for calculating the mass percent of component C. You can do this one of two ways, right? And the easy way would be to just change this to the mass of C right here, and then we can go ahead and change that over to 5.5875 grams, and that will get you 55.44 6% C. But what I need you to be really cognizant of and aware of is that all the percentages, the individual percentages for A, B, and C have to add up to 100%. So that's how you check yourself and make sure that you did your calculations correctly, okay? Always make sure that your total percentages add up to 100, okay? All right, guys, now those percentages that we've just derived, let's use them to give us some more information. So in this particular example, it says if you have 24.4578 grams of the mixture, how many grams of it is component B? Given, of course, based on what we saw before, that component B is 32.295%, okay? So you guys can use the algebraic method for figuring this out, but I always like to teach the dimensional analysis method in chemistry class because it's so essential when we start to change units on you. So as soon as we change a unit on you, if you're doing the algebraic form, you may confuse yourself and arrive at the incorrect answer. So to be consistent, let's learn to think of percentages as conversion factors. So guys, when you see this percent here, it means per 100. So if my mixture is 32.295% of component B, then you can bet your money, let me write it as a conversion factor. If the fact that this is percent per 100, if I had 100-gram sample of mixture, then I know for certain 32.295 grams of it is going to be component B. Do you see how that is a conversion factor right there? So I can go from grams of mixtures to grams of component B, or I can go from grams of component B to grams of mixture. I can bounce back and forth with that conversion factor. But guys, you never start with your conversion factor. I always start with my given in dimensional analysis. So I'm going to go ahead and erase this for a second, and we're going to think and say, okay, what do we got here? We've got 24.4578 grams of mixture. So that's the first thing that I'm going to put here. You always begin with what you are given in the problem. Now, notice I'm going to put multiply, by the way. So multiply here. This is mixture, the X is separate, so be careful with that, okay? So I'm multiplying. Since I have grams of mixture on the top, I'm going to put grams of mixture on the bottom, and I'm going to go ahead and put grams of B on the top, component B. So remember what that conversion factor, it's saying that if I have an arbitrary sample, which is 100-gram sample mixture, you can bet that 32.295 grams of it is going to come from component B. That's what that conversion factor up here tells us. So that way, this allows me to cancel the grams of mixture, and I'm left with grams of component B. Now, guys, should your number that you get, because remember, we don't want to just plug and chug and not even think, right? We want to understand, are we doing something right or not by ballparking it, by estimating it? So look at, you have the grams of mixture here, which is the whole or the part. Think about that for a second, right? So the mixture is, hopefully you said the whole, right? You're trying to figure out the part. And since this is a mass per mass percentage, hopefully the mass of your part, which is component B, should be a number less than 24.4578 grams. You see how that works? So when you actually calculate this, you should get 7.8986 grams of component B, which totally makes sense. If you're calculating this and then your number ends up being greater than 24.4578, then you're like, oh, hold up, something's wrong here, because there is no way that the mass of the part could be what? Larger than the mass of the whole. No way. It's a mass per mass calculation, right? So With that being said, let's go ahead and see how we can use dimensional analysis to go the other way around. So usually students can figure out the part and the whole pretty easily with percentages. Students get thrown off when you think what? Okay, now look, a mixture contains 5.2356 grams of A, which is the part here, and I'm trying to figure out how many grams of mixture, which is the whole here, okay? But guess what? This time we're working with A, so let me put what the percent of A is here just in case we forgot. This is based on the problem that we just did on the previous slide. So that's that right there, okay? It's 12.259% A. Okay. This is still percent, meaning if you had a 100-gram sample of mixture, you can bet that 12.259 grams of it is going to be water, because that's what that conversion factor means. But we never start with our conversion factor, right? We always start with our given. So look at here, we have 5.2356 grams of A. So when you have grams of A on the top, we're going to put grams of component A on the bottom, and we're going to put grams of mixture on the top, because that's what we're trying to solve for. Now guys, who gets the 100 always in percentage conversions? It's going to be the whole. So in this case, look at, I'm going to put the 100 here on the top, because for every 100-gram mixture, I have 12.259 grams of A, component A. So you can flip that conversion factor around any way that you like, except you must always keep the 100 next to the grams of mixture, and you must always keep the grams of the component next to, of course, in this case, grams of A. So that's how you remember you did it right. Now guys, conceptual checkpoint here. We're solving for the part, which means what? Should our answer, we're solving for the whole, excuse me. We're solving for the whole because we were given the part. So should our answer be larger than 5.2356 or smaller? I need you to think about that for a second, okay? And hopefully you said that your answer should be larger than 5.2356 because, again, you're solving for the whole. So you should get 42.708 grams of mixture there. And of course, sig fig wise, this number has 5 sig figs, this one has 5 sig figs, and the 100 does not count because it's exact, right? So that is why I round my answer to 5 significant digits. All right. So let's do some more examples here. So if you're given, now let's actually put chemistry terms in there, okay? So you've got 29.0857 grams of mixture. That contains 4.5890 grams of silicon dioxide. What percent silicon dioxide does this mixture contain? Okay, and then if there's only one other component in the mixture, what is the percent of the other compound in this mixture? So first things first, we're going to do it exactly like we did before. Again, we're just applying chemistry terms here. So we're going to do percent of silicon dioxide here. This is going to be the mass of silicon dioxide, 4.5890 grams, divided by the mass of the entire mixture, which was given to us here in this problem, multiplied by 100. Okay, so this should have given you 15.778% silicon dioxide. Now, in terms of sig figs, I rounded to 5 sig figs because both of these numbers have 5. Remember that 0 that I just pointed to is significant because it comes after the decimal point, after a non-zero number. So you would have 5 significant digits in your answer. Okay, so that was straightforward enough, right? Now guys, how would you figure out if what the percentage of the other component is? You can do it like the long way, and the long way would mean what? Do 29 minus 4.5890. That gives you the mass of what the other component is, granted that you have only one other component, and then you can take that number that you got and you can divide it by the whole again. The easier way is to realize, guess what guys, if you have two components in the mixture, they must add up to what? 100%. Yes. So the easier way for me to do it would be to just be like, okay, 100 minus 15.778, and so that will give you 84.222% of other component in the mixture. So again guys, we're using that critical thinking idea that you know, sometimes you feel like there's missing information in the problem. There's not. Just think a little bit more and you'll be able to derive that answer. All right guys, so let's apply this some more, because a lot of times when you say A, B, and C as components, students are like, cool, check, I get it. But once you start throwing in like calcium carbonate and Tums and ibuprofen, acetaminophen, then things start to get confusing. So do enough example problems in your book to kind of learn to recognize what the part is and what the whole is. So let's look at this one, guys. The average mass of a Tums tablet is 1.298 grams. So the tablet contains 38.2% calcium carbonate. What is the mass of calcium carbonate in grams? So a lot of people think that, you know, tablets are pure substances. They're not. Like medicine tablets are not pure substances. They have the active ingredient in there, which is the calcium carbonate, right? That's what gets rid of your heartburn, right? But it is not 100% calcium carbonate. There's other stuff in the tablet that allows you to digest your calcium carbonate and allows it to be water soluble, so it's absorbed by your system. So guys, when you're dealing with this, learn to see, okay, what's the whole and what's the part? In this case, the tablet is going to be the whole, and then the calcium carbonate is going to be the part. It is the active ingredient. So essentially here, what is the mass of calcium carbonate? I'm trying to figure out what the part is inside the whole. So always start with your given, guys. 1.298 grams of tablet. Okay, so since you have grams of tablet on the top, let's put grams of tablet, which by the way is the mixture, is the whole. If you need to put that a few times, fine, go ahead and do it until you get good at seeing it. Okay, and then we're gonna go to grams of calcium carbonate on the top, which is the part. So guys, who always gets the 100 with these conversion factors when we're dealing with percentages? It's always the whole. And in this case, the 100 is going to go on the bottom because the whole is on the bottom. Notice, a great technique is to fill in your units and then put in your numbers. Okay, so when you do that, the 38.2 grams is going to go on the top, because essentially what we're saying is if you had a 100-gram tablet, 38.2 grams of it is going to be calcium carbonate. So now that cancels, we're left with grams of calcium carbonate. And before you even touch your calculator, I need you to think, should my number be smaller than my given 1.298, or should it be larger than 1.298? And hopefully, since we're solving for the mass of the part in the whole, hopefully that should have been smaller than 1.298. But that is how you checkpoint yourself and you make sure you're doing the math correctly and that you kind of didn't mess up, right? Always, always get the critical thinking skill down and done, because that's how you will succeed in chemistry class, okay? And of course, that ends up being smaller, so check, that makes perfect sense, okay? And it is 4 sig figs, guys. Well, hold on, I should have done that. No. Let's see. This one is 3 sig figs, so let's go ahead and round that up to a 6 right here. There you go. Okay. Yeah, that part was 3 sig figs. Remember, the 100 here doesn't really count because it's just the definition. So I'm basing it on the given numbers. All right. So what about, you know, how we like to do it on tests, right? We change units on you. If you have a pill and you have 80, and this pill is 87.0 milligrams of acetaminophen, which, guys, is the active ingredient in, let's say, Tylenol, okay? So what is the mass of the tablet in milligrams? And remember, I use tablet and pill, you know, interchangeably. So that is your mixture, right? And just knowing that you have 92.0% acetaminophen, the active ingredient, okay, in Tylenol or any other generic pill, right? So always start with your given, which is, in this case, 87.0 milligrams of acetaminophen, which I'm going to put up here is the part. It's that active ingredient in the pill. All right. Since we're being asked to find out the mass of the tablet in milligrams, do you guys, like, some of y'all will try to do, okay, she's been doing gram to gram conversions, so I'm just going to go straight, I'm going to do grams, and then I'm going to come back to milligrams. Don't even bother, right? That's just extra step. Because think about it. As long as you have, let's do milligrams of acetaminophen here, as long as you have milligrams of tablet or mixture on the top, so as long as these two units are the same, you can still use the conversion factor safely. However, don't have grams on the bottom and milligrams on the top, or vice versa. That would give you the wrong answer. So still, guys, instead of pretending I have 100 gram tablet, or I'm going to pretend I have 100 milligram tablet, and in that 100 milligrams I have 92.0 milligrams of acetaminophen. Again, I can do that as long as the top unit and the bottom unit is the same. So you see how that works there? That allows me to cancel, and so I don't have to do extra conversions because both the mass of the acetaminophen and the mass of tablet is both in milligrams. If they're both in the same unit, don't do any extra conversions. So now, guys, since I'm solving for the whole, hopefully that would be bigger than my part. So you should end up with 94.6, and that is milligrams of tablet, and that makes perfect sense because that's larger than the amount of acetaminophen in there, because you expect the whole to be bigger than the part. In terms of sig figs, it's 3 sig figs because both of these numbers, 87.0 and 92.0, have 3 significant figures. Okay? So, guys, now we can do one more variation on this. Of course, there's plenty, but these are the ones that I can think of to help you stay on track and learn the different case scenarios. So this time I give you a mixture. It's 22.85% salt by mass. So I give you that the sample contains 288.5980 milligrams of salt. What is the mass of mixture? But this time I want this in grams. So you can do this one of many ways, but the easiest thing for me is to go ahead and start with my given. So here I have 288.5980 milligrams, okay, of salt. Is that my part or my whole, guys? That's my part, right? Because there's the salt in this mixture. So I'm just going to use whatever units that I started with to do my percentage conversion, okay? So I'm going to go from milligrams of salt to milligrams of, let's see, mixture, okay? Now, you can go ahead and say, okay, for every 100 milligrams of mixture, I have 22.85 milligrams of salt, which is the part. And then the milligrams will cancel. But see, the answer here should be in grams. And always, always, always reread that question in chemistry, because you never know how we change those units up on you. So you can just keep on going, because whatever answer that you got is in milligrams. And whatever you do, some of you will want to do this. Say, okay, 22.85 milligrams in 100 grams. What did I say? You cannot do that. You can't have milligrams on the top and grams, milligrams on the bottom and grams on the top. Whatever unit you choose, I don't care what it is. If it's kilograms, micrograms, nanograms, whatever. It just has to be the same on the top and the bottom when using percentages. But that's okay, because I can, once I do this part, I can go from milligrams of mixture to grams of mixture, and I can tell myself, okay, cool. So remember, 1 gram has 1,000 milligrams in it, and so you see I needed an extra conversion factor here because the mass of my part is different than the mass of my whole. Okay, so that hopefully should have given you 1.2630 grams of mixture or whole. Okay, and the next thing that we want to make certain of is conceptually, yeah, the grams of mixture should have been more than the grams of the part, and that makes sense because remember guys, this is not 288.5980 grams, it's milligrams, which is about what? Exactly 0.288598 grams. So you see how that is bigger than what you started with, and so again that makes perfect sense. And yes, if you did this a different way, let's say that you converted this to grams first and then you used your percentage conversion factor, it would still get you the same answer. I always say there's more than one way to get to Rome, right? As long as you get to Rome, I am so cool with it. As long as you show your work and I see there's a thought process there, that counts as good for me, right? And of course, as you get good at this, yeah, you may come up with a different way of calculating the answer than I would, but it's still correct because you're using those critical thinking skills, okay? That's it for this video. Let me know if you guys have any questions.